Okej, då kör vi igång. Varsågod Gabriella.
So, turbulence. I first became interested in turbulence in my physics class after reading about the butterfly effect. And basically what the butterfly effect is about is that small changes, like the flapping of a butterfly's wings, can create a tornado on the other side of the globe. And I found this very fascinating and decided to learn more. So people associate turbulence with a bumpy flight. But today what I want to do is go into the deeper meaning of what turbulence is. You see, turbulence is everywhere around us. It's in the cars that we drive, in the planes that we fly, and even in our own bodies. So it's very important. But what is turbulence? Well, turbulence describes the way fluids behave. And it's best that I show an example so we understand. As you can see here, and by fluids, by the way, I don't only mean just fluids, I also mean gases such as air, as well as liquids such as blood or even water. And as we can see here, in the beginning, we have very well-structured flow, and that is what we call laminar flow. And then comes the chaos, and it's very irregular and turbulent, and that is what turbulent flow is. So, turbulent flow is most common in nature, that's what we find most, but there is also laminar flow. And laminar flow is, they both also transition between each other, depending on velocity, which is speed, but also viscosity, which is basically how sticky a fluid is. And as we can see here, we did a flow dye visualization, which is basically we have a pipe here with water, and then we put dye in it and watched it flow, which is really cool. There we could see that it's laminar, and here we see that it's turbulent. And in the turbulent flow, you could see that it's mixing, and it's much wider than the flow that was here. And this we use to our advantage, naturally. In a jet engine, the pipes that are found in the jet engine, they are made with basically when the pipes are built, the geometry of the pipes are built so that it promotes turbulence. Why? So that the turbine blades can cool faster. That's important. This is a good advantage, and we use it to our advantage, but there are disadvantages, such as drag. Because when there's turbulence, there's also drag. When we're designing cars or planes, we want it to be a very small amount of drag, because the more drag there is, the more fuel we use and the less efficient. Which brings me to why I believe that we really should learn more about turbulence. Climate change. So emerging economies like China, Brazil, and India, they're all starting to use more technology the same way that we do. And we need to be able to come up with ways that are efficient. So in order to be able to come up with these ways that we can create efficient pipes and so on, we need to be able to model these fluids. We need to be able to understand how they work, which is where the Navier-Stokes equations come in. The Navier-Stokes equations, to say the least, are very, very difficult. They're unlinear. They're really unsolvable. So much so that you cannot solve them by hand, even if they look quite simple. And because they cannot be solved by hand, we use supercomputers. Now, people tend to believe that supercomputers are basically just a faster and a better version of your own computer or PC at home. But that's not the case. What supercomputers are is they're a collection, you could think of them as a collection of computers. and they all divide the task because it's so difficult, and they solve it, and then they report back to the central system. And in fluid dynamics and in turbulence, we use it to be able to model how we think fluids should behave. And this is called DNS, direct numerical simulations, which I'm going to come to in a minute. And yes, but what we also do is that, because these are so difficult, as I said, we use experiments. And what I used was the MRI. So here we could see my setup. There's a pipe that's about 8 meters long. And then we have our MRI here, the compact MRI. And we use this to study the flow. Now, how can you study flow with an MRI? I thought it sounded weird in the beginning. But this is how it works. So atoms, they have this characteristic called spin. And basically, they act as magnets. And an MRI is just a huge magnet. So once you put the fluid in the MRI, they start to align themselves. Some align north, some align south of the magnetic field, and some don't align at all. They're unmatched atoms, we call them. And those unmatched atoms, this is after they're in the magnetic field. And so those unmatched atoms are radiated with radio frequency waves. Once they're radiated with radio frequency waves, they align themselves magically. And once they've aligned themselves, we turn off the waves. Once we turned off the waves, they release this energy that they just absorbed. And based on their position, and based on the amount of energy that they released, we create an image. So using that data, we create velocity profiles, which is what we've been doing. Now we can think of the box, the borders, as the pipe. You can think of it as if it's horizontal, like this. And we could think of these curves that are here as the streamline, so that's the water that's flowing through. And as you could read here, the boxes are the experimental data, and the red line is the theoretical one, and here we use the supercomputers that I was talking about, DNS results. And as we could see, the experimental data and the theoretical data correspond quite well. Of course, we can't say that they correspond completely, because there is deviation here, and we see deviation here at the peak as well, and there is deviation here as well, but it's less in the turbulent flow. So, although there is deviation, we can see that the MRI is a good way of being able to study how flow works. And basically what all these points on the graph are is, what is the speed of the water at different points in the pipe. So as I said, this whole thing is a pipe, and then what's the speed here, 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 and here, and here's the relative speed, and there's the relative diameter. So the conclusion we came to was that Navier-Stokes equations are hard, and we can use the MRI to be able to somehow understand how fluids flow and be able to develop methods that are useful. Yes. And the deviation could also be because of the pipe itself, the roughness of the pipe, or other reasons as well. Lastly, I would like to thank my amazing mentor. I had an absolutely amazing time at KTH. It was really, really fun. As well as Professor Luca Brandt for allowing me to be there. And Kjell och Märta Bjerres Stiftelse and Teknikföretagen, which are Ray's collaborative partners that made this happen. And Race for Excellence and the amazing people for making the summer so much fun. Thank you very much.